So to quickly review what we've been doing for last class. So we started looking at the noise of the different sources in the mixer and finding out how they translate to the output. So the previous class we had looked at the load noise. So you had either the resistor or maybe a common mode feedback loop with a PMOS. That was pretty straightforward to analyze. It directly adds to the output. The next stage we started looking at was the noise from the transconductance stage, and we took the simplest example of just a common source transistor and we started looking at the noise. So we have flicker noise as well as thermal noise in this transistor, and we suggested that the mechanism for conversion or the mechanism in which the noise of this transistor appears at the output is the same as what you observe for the signal. In other words, you will see mixing of this noise at the when you go from the RF port to the IF port of the mixer. The big difference is that the RF signal itself was narrow band, therefore it was available only in a small range of frequencies, whereas thermal noise is actually broadband, so you do have it at many other frequencies. And fundamentally what we observed is that apart from thermal noise at the RF frequency going to the IF frequency, just as you would see for an RF signal, you also have noise from the image band. Now you also see, because the LO signal also has components at 3 omega LO, 5 omega LO and so on, you will also see noise from around those 3 omega LO and 5 omega LO components mixing down to IF. So if you look at the overall noise at the output, the overall noise can be observed as 4 kT gamma by Gm times the gain of the mixer squared, which is 2 by pi Gm RL squared. This is for a single balanced mixer, times, if you look at the noise coming from each one of these, this is nothing but 1 plus 1/3 squared plus 1/5 squared plus so on, times 2, because you have both upper and lower sidebands. And as it turns out, this whole quantity, overall quantity, is pi squared by 4. Twice 1 plus 1/3 squared plus 1/5 squared plus so on is pi squared by 4. And therefore the overall noise is 4 kT gamma Gm RL squared. Now the nice thing about this is that if the RF transistor or the transconductance stage has flicker noise, that does not directly appear at the output, because the RF noise would get upconverted around omega LO, 3 omega LO and so on. Finally, if you have a transmit mixer where the output frequency is the high frequency component, is the LO component in a direct conversion transmitter, you are worried about 1 over F noise being upconverted from the transconductance stage. Finally, we started looking at the noise from the switching pairs, and this was a little bit more complex to analyze. So we said we are going to replace the noisy switching pair with the noise being referred to the common gates of the input of the LO port as a single voltage source, a single noise source. And we also said such a noise source will only serve to change the switching instant of the differential pair. And at the instance of switching, we can actually replace the real square wave, which has a varying switching instant due to noise, with an ideal square wave plus a series of pulses. The pulses could be positive or negative depending on which edge you are looking at and how the noise changes the switching instant. So this SR of t is the ideal S of t plus the pulse train P of t. This pulse train is not an impulse train, it is just a train of these small narrow pulses. If you look at the output current of the switching pair, this pulse train will actually give you an output current pulse train of height 2 I of t, because the differential current is the current is switching from plus I of t to minus I of t. So the height of the pulse will be 2I of t, and the rate of the pulse train is going to be twice the LO frequency, because this happens at every edge. And we have already derived that the width of the pulse, delta t, depends on the slope at the zero crossing. So it is Vn of t by s. And if the input is a sinusoid, you can actually calculate the value of the slope in terms of the amplitude and the LO frequency. And now to find out the noise transfer function to the output, we figure out the average value of I out over one period and in terms of Vn, and that gives you something like this, but this only gives you the low frequency component. We know that this pulse train actually has a rate of 2 omega LO. Therefore, you have an output current spectral density which looks something like this, right? So you see flicker noise at low frequencies and also as skirts around 2 omega LO, 3 omega LO, 4 omega LO, and so on. Is that clear? Now what I'm going to do is I'll kind of start off, but it's a little bit more mathematically complicated. So I'll give you the reference to the paper. If you want to know the exact details, you can go ahead and read up the paper as well as its references. But since it is out of the scope of this particular lecture series, what I'll do is I'll give you the final result also and approximately how you arrive there. You can go look up the reference and read it up. So the reference for all of this noise analysis is noise in RF CMOS mixers, a simple physical model. And this is from the IEEE Journal of Solid State Circuits, pages 15 to 25 in Jan 2000. Okay. So if you want further results, further understanding of how you come up with the results we are going to arrive at in today's class, you can read up this paper. So the idea is the analysis is similar but slightly different as what we did for the flicker noise. So let us say this is the voltage noise Vn as a function of time. This is Vn of t, and we said if you actually look at the output current noise, okay, so it is going to look like, what is it going to look like, the output current noise? It's going to look like a series of pulses of varying width. That's what we said. And at rate, and the rate of the pulse is going to be twice the LO frequency. The height of the pulse is 2IT and the rate of the pulse is twice the LO frequency. What is the width of the pulse? Is delta t. This is varying from every edge, for every edge. Now what we are going to do is we are going to replace this pulse of a constant height but varying width by a set of pulses of constant width and varying heights, such that the same amount of noise is observed. So we are going to say the height of these pulses, the width of these pulses is constant, Ts, Oh, sorry. In fact, what I'm going to do is, instead of just putting it as positive and negative pulses, I'm just going to replace it with a pulse train. Okay, multiplied by Vn. Okay, such that I get the same output noise. What is the height of these pulses? That will depend on Vn, right? Or rather, you can make sure, if you, okay, so it will be a function of Vn, but the minute you have actually taken out Vn, this pulse train will have a constant height, which is just a function of what? What is delta t a function of? It is a function of Vn, but also the slope at the zero crossing. So if you look at the height of these pulses, this will end up being 2it by sts. Okay? Because delta t, what is the value of delta t? It was Vn by s. Right? So if you are going to take out Vn as a common factor, the height of these pulse trains will be 2it by s times ts. So ts is defined as the time, so ts is the switching time when both the transistors are turned on. Okay. This is not something you choose. This is something which, if you, when you design your LO pair, you can actually find out how long they take to switch. This is calculated from the IV characteristic of the switching pair. So, for example, if this was VID, this was IOD, the output current is going to look something like this. It goes from minus IT to plus IT. Okay, the current goes from minus IT to plus IT, and this is delta V, which causes that current switching. So in other words, we are actually doing a piecewise linear approximation. Okay, and we can do this because the delta V is very small, because the noise is much smaller compared to the LO signal. Because delta V is much smaller than the LO signal. And if you need to generate the transconductance from this, how do you generate it? So I'm just going to copy this figure. If you get a VID, the transconductance will look something like this. This is your GM of V or GM of delta V, where this is delta V. What is the height of this? This is nothing but 2IT by delta V. Okay. Now, if you had to look at this transconductance as a function of time, what would that look like? So what you are really interested in is GM of t around the switching instant. That will be the same as GM of delta V, because it's this delta V which is causing the change in delta t. So delta t, since delta t is related to delta V, therefore this will also be the same as GM of t during the switching time. Okay, so again we'll say so let us say VID was 2 VLO cos omega LOT. GM, rather first let's calculate TS. TS is delta V by S, which is 2V LO omega LO. This is the delta V by S. GM is 2IT by delta V, and we'll rewrite this as GM of t. So what we did was we said we are going to replace this with GM of t. The switching time is TS. What is the height of this pulse? 2IT by delta V. So your GM is nothing but 2IT by delta V. What is this? 2IT by STS. Okay, from this relation. So now the output noise, or rather the input referred noise spectral density of this, the squared voltage noise density, will be related to the transconductance, right? Because this transconductance is related to the small signal transconductance of the device during this switching instant, and therefore this will be 4kT gamma by GM. If you were looking at a small signal transfer function, it would have been, the input referred noise would have been 4kT gamma by small gm. Now it is 4kT gamma by large gm. This is the spectral density. And now I'll just say it can be shown that, because I don't want to go through the mathematics here. The output noise due to the switch, if you follow the procedure given in the paper, 2 by T LO times 2IT by S squared times 1 by TS times Vn squared. So if you actually plug in all the quantities, you get this is for a sinusoidal LO signal. Okay. So the total noise, output current noise, is 4kT gamma times IT by pi VLO. Now the first thing which should strike us is that this does not seem to depend on any device parameters. Right? It seems like this noise seems to be independent of the switch, and it depends only on the tail current and the LO amplitude. Okay. This is because if you, I think we touched upon this yesterday when you were asking why it does not add broadband noise. So in reality, if you actually try to make the device switch faster by increasing the device size, what happens is this value drops because the large signal GM, the piecewise linear GM that you have derived, becomes larger, and therefore Vn squared actually becomes smaller. But because the pulse widths are actually much narrower, you are actually sampling more broadband noise. So if you increase the device, you actually have lower input referred noise, but you are actually pulling in more of the noise. Whereas if you make the device smaller, what is happening is you are actually increasing the input referred noise, but you are actually, since it's switching much slower, you are actually folding in lesser of that noise. So let us say this was the FLO, sorry, 2 FLO, 4 FLO and so on. So this represents your broadband noise. So I'll maybe use a blue color marker. So what we found was that noise from these points actually makes its way back to FIF. Noise from all of these make their way back to FIF, but this is actually sampled by the pulse train. What is this point? It's 1 over TS, right? It's FS, which is 1 over TS. So if you make this TS instant, the time for which it's sampled much smaller by increasing the device size, what happens is the amount of broadband noise which is folded down increases, but the actual noise floor itself will decrease. So now that we have figured out what the different noise sources are, we just have to add up all of these to figure out the overall output noise. So let us say this was a simple load resistor. So the noise due to the resistor was 8 kT RL. The noise due to the GM stage was 4 kT gamma GM RL squared. Plus the noise due to the switch is 8 kT gamma RL squared times IT by pi VLO, because this is the noise due to one switch. Since you have two switches, you will have to double this. So I'll rewrite this as 8 kT RL 1 plus gamma GMRL by 2 plus so first of all, the thing to note is that if you want to reduce the noise from the switch, you have to have a very large VLO, right? If you drive it with a sinusoidal. But even otherwise, the larger you make VLO, the faster the differential pair will switch. But you also know that that makes your linearity much worse because of the displacement current. So now we want to optimize this noise. So if you want to optimize the noise performance of the mixer, So what you have to do is, you will have to, so let us do one thing, we will rewrite Gm in terms of the VGS minus VT of the transconductor. So the VGS minus, the Gm of this device is nothing but IT over VGS minus VT plus the last term is gamma RL IT by. Why do we want to do this? Because the noise from the switches is in terms of IT and VLO. We can rewrite the Gm of this in terms of IT and VLO and compare the two. So if you look at the relative contribution of the switches and the transconductance stage, the ratio of these two is, 2 VGS minus VT by pi VLO. So if you try to make these two quantities almost equal, right? If you make this approximately 1, you will get equal contribution from both the switch and the transconductor. VGS minus VT has a direct bearing on the linearity of the transconductor. So when we say noise optimum, we are saying optimization of noise while keeping linearity in mind. Now we are done with what is the direct switch noise, which is the noise which is modulated by the switching of the differential pair themselves. We also talked about a second source of noise, which happens when the differential pair has a parasitic capacitance at the common node. I'll call it's called the indirect switch noise. So let us say the common source node has some capacitance Cp. Okay, and we have pulled out the noise as some Vn, the input referred noise. So this is VLO plus, this is VLO minus. Now what do we know about the switching pair? During 1/2 cycle, the switching pair, let me call this M2 and M3. During the first half of the cycle, M2 is on. During the second half of the cycle, M3 is on. Okay. During that time, if you actually have a capacitance, the cascode will give you some frequency dependent noise. Now, the way we are going to analyze this behavior is by replacing this with a single-ended cascode type stage. The only difference is, you notice that the right side switches perfectly, whereas the left side does not. Right? The right side has a perfect switching waveform, whereas the left side does not. So we are going to replace that. So if we had VLO plus and some Vn, I am just going to draw a current source here, Cp, and during the second half cycle I actually have VLO minus here. This has 2 half cycles. Okay. Now I am going to make a further modification. I am going to replace this with a single pair of transistors. Okay, this is your current source and Cp, except I'm going to make a small change here. I'm going to make this VLO, where the signal here this signal here goes from 0 to Vn and back to 0. So it is as if you are sampling your Vn with an LO signal and applying it at the input. Okay, so during the positive cycle you apply Vn, during the negative cycle you apply 0. So since Vn is much larger than VLO, you can assume that the system is linear, first of all. So linearity is valid. What is the time constant at this node X? This is M23. The time constant at node X is given by, the time constant X goes as, what is it? Cp by Gm23. Okay, and the assumption also is that if the parasitic capacitances are small, and because this Gm23 may be large enough, this is much smaller than the LO time period. Okay, in other words, what we are saying is that node X is charging and discharging much faster than the LO frequency. That is normally a valid assumption. So if that is the case, this node X is going to charge and discharge periodically during every period, during every crossing, during every zero crossing. Okay, and if you actually look at the waveform, Vx as a function of time, you are going to see some exponential charging, and then for the rest of the period it stays constant. Exponential discharging stays constant, exponential charging, and so on. Here this is TLO. Now from this we can actually derive the current through the capacitor Cp. That is going to look like a current pulse. And so on. So it has a frequency of FLO. Obviously the DC current through the capacitor should be 0. So it has a 0 DC value. However, if I look at the output differential current, what will that look like? Look like this. It will look like this, because the same Cp is being switched from between either side, and when you take the differential current, the negative values will get flipped over to the positive side. What is the frequency of this? 2FLO, and it has a finite DC value. What is the value of this DC? Zero to TLO by 2 ICP of T dt. The current through the capacitor is Cp Okay. Vx of TLO by 2 minus Vx of 0. How much is that? What is the? It is just Vn. The reason you have this pulse is because of Vn. Okay. So what this means is, this gives you the effective gain from the input of the at the LO port, from the input referred noise at the LO port to the output noise current. The conversion gain is which is 2 FLO-CP. Now the interesting thing is that the conversion gain is actually proportional to the frequency of the LO. Okay, so if your LO frequency gets larger and larger, the effect of this capacitance will also become more and more prominent. Okay, and now of course you can add this to the overall output noise and optimize it further if this CP is important at your operating frequency. Okay, so we have looked at all the different kinds of noise effects. Now we did discuss some amount of something related to linearity of the mixer itself. So now, knowing what all you need to know about the noise and linearity of the mixer, what can you do to improve the mixer performance? Some simple circuit techniques to improve the mixer performance. For example, let us go back a couple of classes ago. So we had a resistively loaded single balanced mixer. Okay, what was the problem with the resistively loaded single balanced mixer? The problem is that there is a direct relationship between the headroom, the output common mode, and the bias current you are going to use in the mixer. How can you fix this? So what do you want here? I want some IT. Okay, so IT by 2 flows through each of RL. So the drop across RL is ITRL by 2. Correct. So one simple thing we can do is add some extra current, I'll just call it I0, okay, such that we only have a very small current flowing through RL and most of the current is being supplied by this current source. This current source will just be a PMOS transistor, doesn't need to be anything extra. Anything about current sources? Current source noise will come in. But if it's just a simple PMOS transistor, what would you try to do to reduce the noise? For a current source, if you want to optimize the noise, you should reduce the GM, right? Okay. If you try to reduce the GM, what happens to the device size and current? The device size will become very small, and for a given current, the current may be fixed because there is an upper limit on the amount of current which is IT. Right? So what happens to the VGS minus VT of these devices? It may get very large, okay, but it really is a function of I0 and IT. What happens to the output linearity? Ideally these devices should be high impedance and they should be ideal current sources. However, remember that you are going to be experiencing some swing at these nodes, okay. And when these nodes swing, you will need to maintain these current sources I0, extra current sources I0, the PMOS devices, in saturation region. So linearity could be an issue. On VT of I0 devices. Okay, anything else? Can you do something better? Make it virtual ground. Make what a virtual ground? Make the output nodes a virtual ground. And take the current. Okay, yeah, that is something we can do, but we are assuming that we are taking a voltage output. Definitely, you can make the output, send the output into a virtual node by tapping the signal current instead of the signal voltage. That will help a lot. In that case, you don't even need the resistor RL, right? You can use many different kinds of circuits. So let us look at this current tapping. Is there any other node where I can actually add this I0 current source? What about node X? Can I add it at node X? What are the advantages and or disadvantages of this procedure? So let us look at an alternative circuit. Okay, so let us look at this. Suppose I add some I0 here. What are the advantages or disadvantages of this? Well, the advantage is the current source no longer limits the linearity at the output node. The output can swing as much as it used to. And you have also managed to break this connection between IT and the output common mode. Correct? So this is doing exactly the same thing as before as far as output common mode goes, but the current source is no longer impacting the output linearity. Anything else? What about the LO devices? What decides the current through the LO devices? In the earlier case they were just IT by 2 each, now they seem to be much smaller. Is there a problem with reducing the current through through the devices? What does this depend on? The output noise due to the switches depends on the current through the switches. Correct? This IT was what was flowing through the switches earlier. Now this will not be IT but IT minus I0. Is that a good thing or a bad thing from the point of view of noise? It's a good thing. Now one problem with this is that you are actually increasing the parasitic capacitance at this node by adding this large current source. Okay, because this PMOS current source will have a large fixed capacitance which will be the drain bulk and drain gate capacitance, and not necessarily because this is a current source, right? You may not even be using minimum length devices. Okay, so therefore this current source could actually dominate the capacitance at that node. And a second effect is that by reducing the GM of the switching pair, by reducing the current through the switching pair, you are reducing the GM LO, correct? What effect does that have? The time constant at this node was a function of the GMLO. It was related to CP over GMLO. Okay, so you have actually increased the time constant of charging and discharging of that node. That could also make the indirect noise worse. Finally, the way your RF current splits between these two parts is relative to the impedances of CP and GM of the LO devices. If GMLO decreases and CP increases, you are pushing more and more of the RF current through this path, okay, compared to the primary path. So you have to be very careful when you use such a extra helper current source in your design.